Having understood your stress matrix, it's quite necessary to understand your strain matrix as well. So starting with your 3 dimension, so we need to show this 3-dimensional strain system. It's just analogous to your stress system. So here along the diagonal we'll be having your normal strain represented with epsilon, and rest other elements will be your shear strain. Here we represent it with phi. And one thing is different out here, that is with all these shear strains a factor of 1/2 has to be multiplied, or all the shear strains have to be divided by 2. And why it is getting divided by 2 you will come to know when we'll enter more into deep of this subject called strength of materials. But for the time being, please do remember this is the representation of your strain system or strain matrix. Okay. Similarly, we have got this x, x, xy, xz, yx, yy, yz, and zx, zy, zz. Now, in order to show this strain system, we have taken a cuboidal block or cubical block, and we show this stress system sigma x, sigma y, and sigma z. Now, due to this sigma x, sigma y, and sigma z, there will be some normal strains generated or produced in here. So let us consider the strain, normal strain along x direction. So the effect will be due to x, due to y, and due to z. Of course, we have studied this, what is your lateral strain and linear strain. So in order to incorporate all those concepts of your normal strain and the Poisson's ratio and your lateral and linear strain, your epsilon x will be given as sigma x by E minus mu times sigma y by E minus mu times sigma z by E. Why this is negative and negative? Why? Because say if you are pulling something along x direction, then of course in the opposite 2 directions, that is perpendicular 2 directions, maybe in y direction and also along z direction, what is going to happen? There will be decrement, that if there is elongation or increment in the length along x, then of course there will be decrement along y and there will be decrement along z. That is the concept. So this is generally for common standard material, but yes, exceptions are there. We will study all those exceptions sometime later, but for the time being, which is a normal material in which if you are putting some elongation on one direction, then of course there will be some compression in other 2 directions. So we have epsilon x equals to sigma x by E minus mu times sigma y by E minus mu times sigma z by E. Similarly, we have epsilon y is given as sigma y by E minus mu times sigma x by E minus mu times sigma z by E. Now epsilon z will be sigma z by E minus mu times sigma x by E minus mu times sigma y by E. Now these were the normal strains along x, along y, and along z. Now if you are interested to find the total strain, then of course you need to add all these 3. Now once you add all these 3, you do the algebraic sum of all these, you will get a very beautiful expression as sigma x by E plus sigma y by E plus sigma z by E whole multiplied by 1 minus 2 mu, where mu is your Poisson's ratio. If we reduce our dimension from a 3-dimension to a 2-dimensional, then in that case your z component gets omitted, and you can represent the diagram like this. We have 2 coordinates, that is x and y. So along x we are showing your normal stress, which is sigma xx. Along y we are showing the normal stress, which is sigma yy. So epsilon x will be sigma x by E minus mu times sigma y by E, and epsilon y will be equal to sigma y by E minus mu times sigma x by E. Alright. Now if you add these total epsilon x, epsilon y, you will get the total strain, which is sigma x by E plus sigma y by E multiplied with 1 minus mu. And in terms of matrix, you can represent like this. Okay, so here we were having a 3-dimensional matrix, that is 3 cross 3 square matrix. Now if you remove this z component, so this column gets omitted, this row gets omitted, whatever is remaining out here is these 4 elements. So these 4 elements are present here, removing the z components. Now further, if we reduce this 2-dimension to a 1-dimensional stress system, in that case we can represent the diagram like this. We have sigma x in this manner. Now you can show this epsilon x as sigma x by E into 1 minus mu. Of course there will be single strain along x, so this total strain is nothing but your epsilon x itself. So here we have got epsilon is equal to sigma x by E multiplied with 1 minus mu, and here we need to remove this y components as well. So from this this 2 cross 2 matrix, we need to omit this y component, y column, and here we need to remove this row containing the y component. So what we are left with is your epsilon xx, that is your single element in this particular matrix. Now you need to note one important thing, that how to consider whether a shear strain is a positive or negative. So let us consider we were having some original shape like this. Now due to some deformation, the deformation goes like this. If this diagram appears, then understand it is a case of positive shear strain, where it is making a uniform angle on this side and this side. So this angle is 90 minus phi, and this angle is phi by 2, this angle is phi by 2. Now if you compress this, or rather if you if you observe that this shape is getting converted into some shape like this, where this angle is also again, which is phi by 2, phi by 2. So whenever this shape appears, then understand it is a case of a negative shear strain, and whenever this shape appears, then understand it is a case of positive shear strain. So that's it. These were the important things that we discussed under the topic called strain metrics. See you in the next lecture. Till then, bye.